Okay, so yeah, not everybody's here today, and some of you will get your exam back on Friday, but I do have them for you. So tell me if you're here, Nate Barfield. Yep. Daniel Smith. David Johnson, or Johnston? No. Yeah. Austin. Ian. Sarah. Alandra. Alandra? Oh, that's you. Isaac. Blake. Janessa. Lily. Ethan. Scott. Austin. Davis. Kenny. Has everybody got an exam? Okay. And your name? Did you take it on Friday? Yeah. Okay, just so everybody knows, the average was approximately 76%. So I'd say maybe that's a couple points lower than this exam maybe usually averages, but pretty much on. So yeah, not bad overall. There were several A's, lots of B's, lots of C's. So what I would suggest is that you do figure out what you did do wrong and kind of figure out how to fix your mistakes, because this kind of stuff will keep coming up in the sections to come. Like, it's not the last time that you might have to like calculate a solid of revolution or something like that. So just be aware and make sure you know what you did wrong. That said, let's talk about some homework questions. So I think that there's been a little bit of confusion, and I apologize for that, around the videos and then the homework. The videos, I talk about like section like 7 point something, but then the homework is in chapter 8. And what happened is that was recorded in a different edition of the book. So when I recorded that, it actually was chapter 7 that I was covering when I was talking about like basic techniques of integration, like for today, or integration by parts, or whatever the case may be. But chapter 8 is right for your homework. Okay, so on the videos, don't worry so much about what I say the numbers are or the sections are in the videos. What matters is what was assigned for that topic, and that is right. Okay, so just wanted everybody to know. All right, any homework questions? Yes, sir. 47 on 8.1? Okay. Interesting. Okay, this is number 47. And we've got the integral dx over x to the minus 1 plus 1. Okay, and it's kind of like this is the section of being clever, right? If you can find a clever way to do things, it will make your life a lot easier. So, well, first of all, x to the minus 1 is kind of terrible in some sense. I don't know exactly how to work with this right now, so we could rewrite it. So we could say this is dx 1 over x plus 1. Right, is the same thing. We could combine those two into one fraction. If I did, I'd get the integral of dx is on top, and on the bottom we have, this is x over x, and this is 1 over x. So this is 1 plus x over x. So now we have like a 1 on top and a fraction on bottom. I could flip and multiply. Agreed? So this could be written as integral of x over 1 plus x dx. Okay, and now the question is this even any better? I think it might be, but this is, how do I want to go about this? One thing I could do here is U substitution's not, well, let me think. Do I like it? Nah, not really. I think that U substitution is just kind of get me back where I came from, but maybe not. What I could do though that I do like is polynomial division. Okay, and that was one of the techniques that we covered. So what I could do is just kind of jump over to the side for a second and say, all right, how do I divide x by x plus 1? So I want to divide x, that's what I'm going into, and I want to divide into an x plus 1. So I say, how many times does x go into x? 1. So 1 times x plus 1 is x plus 1. Then I subtract. Right, and so x minus x is 0, and then I get minus 1. Okay, so all of this to say is it goes in 1 time evenly, and then I have a minus 1 left over that's still being divided by x plus 1. So in other words, the way that I could write this is it's 1 minus 1 over x plus 1. So I could rewrite this integral as the integral of 1 minus 1 over x plus 1, all of that dx. Now, do I know the antiderivative of 1? Yes, I do. Do I know the antiderivative of 1 over x plus 1? That's a good question. The answer is yes. What is it, though? Well, if I U substituted for x plus 1, I don't need to, but I'm just explaining what I'm doing. Then what would be the derivative of x plus 1? 1. So the derivative of the bottom is sitting on top. When I have the derivative of the bottom on the top, that's a natural log. Okay, whenever f of x is here and f prime of x is here, that's natural log of whatever it is that's on the bottom in absolute value. So this is equal to x, because that's the antiderivative of 1. The negative can just stay around, and then I get the natural log of the absolute value of x plus 1 plus c, because this is it's indefinite integral. And that's it. so we can do it. Yeah, so just a little bit of manipulation, a little polynomial division, and we get there. Sound good? Any questions? Any other questions? Or about this? Yeah. 45. Let's see. 45. So 45, we have the integral. On top, we have e to the x. On bottom, we have e to the x minus 2e to the negative x. 2e to the negative x dx. All right. Well, there's a couple different things I can see that we could potentially do here. The question is, which one do we want to do? I almost feel like I could turn this problem into this problem with a u substitution. So let me show you what I mean. So if I let u be e to the x, then du would be e to the x dx. So here's an e to the x, here's kind of an e to the x, it's an e to the x on the bottom, right? And then here's the e to the x dx. So if I made a substitution using this u, then on top I get e to the x dx becomes du. And on the bottom I have e to the x, which is u, minus 2 over e to the x, which is u. And now that looks very, very similar to what I had here. It's not exactly the same, correct? But it might end up being similar. So I could rewrite this as integral du over, this is u squared over u, right? So I've got u squared over u minus 2 over u. So I could write that as the integral du. And on bottom, I have u squared minus 2 divided by u. So now I can flip and multiply, and I get that this is the integral of u over u squared minus 2 du. So far, so good. Here, this is a u substitution problem, correct? Because I want to substitute for u squared minus 2. So here, if I let w equal u squared minus 2 and dw equal 2u du, I'm very close to having what I need. I need a 2u du. I just have u du. So I could put in my 2, put in a 1/2 outside to cancel that out, and now I could make that substitution. So here we go. Over here, I still have that 1/2 sitting outside. Inside, I have 2u du, which is called dw. And on the bottom, I have w, correct? And what's the antiderivative of 1 over w? Yeah, the derivative of the bottom is the top, right? So it's ln of absolute value of w. So this is equal to, the 1/2 just stays, and the antiderivative is ln of absolute value of w plus c. But that's not what we want. We want x's, right? So we have to say, well, what is w? W is u squared minus 2. So I could say that this is 1/2 ln absolute value of u squared minus 2 plus c. That's better, but not what we want. We want x's, but u is e to the x. So this is equal to 1/2 ln of u is e to the x. So we have e to the x quantity squared minus 2 plus c. And that's right. So again, nothing that we're doing in this section actually is new. It's just tricky, right? So what they're doing in this section is kind of saying, hey, you know some stuff, but let's see if you can do something kind of fancy with it. So you should always be thinking, these are hard problems, and I don't expect that, like, I've had some experience, right, doing this kind of thing. And so I can look at a problem like this and I kind of be like, okay, I know what to do. I don't expect you to be able to do that. I think you'll try some stuff, it will be wrong. Then you'll try something else, and that also will be wrong. And then hopefully, eventually, you'll be like, oh, yay, I got it. This is it. So try stuff is my recommendation. Try it. It's like, well, would a U substitution work? Would polynomial division work? Would completing the square work? Is there a trig identity I can use? Just start trying stuff until you land on something that works. They're challenging problems for sure. Other questions? I see somebody saying something here. Oh, somebody said that 8.1 number 47 isn't one of the problems listed.
I realize that.
Oh yeah, well, it's still good times, right? It's still a good example because actually that one is pretty similar to this one. But yes, that is true. Did you say 25? 29, okay. Yes, this is the 8.1 homework.
Yeah, I was just looking, and for where we turned in, none of these
I don't know. I mean, it's been up there for a little while. Yeah. I think it's that you might need to take another look. Show me what you're talking about after if, but it should be there. Yeah. Okay, I'll have to take a look at that, but it is a sign. Okay, and you said 29? 29, we have integral from pi over 4 to pi over 2 of the square root of 1 plus cotangent squared of x dx. Okay, any ideas? Here's something that I would assume that everybody's pretty familiar with, that sine squared of x plus cosine squared of x is always 1. Everybody buy that story? Yeah, I feel like this is like the well-known brother of like 3 brothers. There's 2 other brothers too, but no one remembers them. It's sad times. But what you could do is, like, let's say that I divided everything by cosine squared of x on both sides. So what's sine squared of x divided by cosine squared of x? Sine over cosine is tangent, so that would just be tangent squared of x, right? Cosine squared of x divided by cosine squared of x is 1, so plus 1 is equal to, well, 1 over cosine squared of x is otherwise known as secant squared of x. So here's the second brother. The other one is when I take this thing and I divide everything by sine squared of x. So sine squared of x divided by sine squared of x is 1. Cosine squared of x divided by sine squared of x is, well, that's cotangent squared of x, right? This is looking familiar. And finally, 1 divided by sine squared of x is what? What's 1 over sine? We call that cosecant. So this is cosecant squared of x. So these are actually all the same equation. They're just like brothers. But once in a while, one of them is the most useful. This time, this guy, right, is the most useful. And so we can replace this with what it's equal to, which is cosecant squared of x. So if I do, I can rewrite this as pi over 4 to pi over 2 of the square root of cosecant squared of x dx, which of course is just integral pi over 4 pi over 2 of cosecant, cosecant of x dx. Okay, cosecant of x. The question is, do we know the antiderivative of cosecant of x? So what is the antiderivative of cosecant of x? Do they?
It's negative cosecant x.
Well,
I've got that in my differentiation.
yes, and you are very right if we were taking a derivative.
Oh, that's the derivative.
Right? Yeah, that is the derivative. I'm saying, okay, so what's the antiderivative? That is harder. Taking the antiderivative. I'm kind of wondering, because we do cover this. I know how to do this antiderivative, but I'm trying to do it with just the things that you know how to do. It would be nice to look at. I'm trying to decide. Okay, it's not the worst idea. The problem is, okay, so this is what everybody feels good about, and I don't blame you. This is 1 over sine x dx. And everybody feels happier because they like sines better than cosecants, and I don't blame you. They are better. But now what? And so a suggestion was, what about a u substitution? Unfortunately, well, what do you want to substitute for? If you substitute for the sine, then you need a cosine, right? Because you need a du. And if you substitute for 1 over sine, that's not so great either. Just a second. So this was 29. How do they want you to do that? That is interesting. Say that again. The 1, like here? Oh, here. So you're saying turn it into like a sine squared of x plus a cosine squared of x. It's not my favorite thing, but let me think. don't think so. But let's, but it's not the worst thing I've ever heard. So let's do it. This is the kind of thinking you need to do on these problems. So it's worth it. So let's go ahead and say this is an integral from pi over 4 to pi over 2. Sometimes it's a disadvantage to know how to do it, because now I'm like, well, there's no other way to do it but the best way. And it's kind of like, so it's harder for me to see the right way. Okay, the one you said is sine squared of x plus cosine squared of x over sine of x dx, correct? It's not the worst. It actually is kind of good, because what we can do is split that into 2 fractions. And then this one is just sine x, which is wonderful. And then the other one is cosine squared of x divided by sine of x dx. This I can do. This still seems like a bit of a mess. What is that? I suppose that is cotangent of x times cosine of x. And if I use sub for sine, I get a cosine, but I really need 2 cosines. If I use substitute for cosine, that's no good, because then I need a sine, but I only have one on the bottom. Yeah, just a second. It couldn't be that. I hope it isn't at least, because that's really mean. I don't know. I don't remember this problem. Okay, let's keep going though. I'll tell you what I'm thinking, and maybe it's total nonsense, but let's keep going. Okay, so I've got integral. Of course, it still has its limits. Okay, so sine x is good. I think we've established that. Cosine squared of x could be written a different way because of that. What is it? Cosine squared of x is otherwise known as 1 minus sine squared of x. Agreed? So I could say that this is plus 1 minus sine squared x divided by sine x, all of that dx, correct? And it's kind of like, well, that seems bad. Maybe. The jury is out. Let's keep going. Now I could split it into 2 fractions, correct? So one of them, so the sine x is still hanging out. Then if I split this into 2 fractions, I get 1 over sine of x, correct? Which is very disappointing, but let's keep going anyway. 1 over sine x. And then I also get what? Negative sine of x. That is weird. Okay, it's okay. So the sine x and the negative sine x, I suppose, sort of cancel. And what do I get? Exactly what I started with, which isn't really that helpful. Yeah, so that didn't work. All right, well, worth a try. That happens sometimes. So what do they want you to do with cosecant of x? That is a challenge right there. It's definitely what they wanted you to do. Cosecant. I hope they didn't just like throw those antiderivatives in this section just for kicks and say, this is what they are. But they might have. What's that? Where? Oh, you mean in the answer? No, I know how to get the answer. It's just, it has to use integration by parts, which is the next section. So I'm wondering, how did they, this may be a mistake in the book where they shouldn't have asked this question yet. Oh no, that's what I was afraid of. Just a second. Painful. Okay, yeah, this is exactly what I was fearing. On page 520 in your book, many of you don't have your book, but it says the following, and this makes me very mad. It just says, hey, here's a formula. Integral of cosecant of ax dx is equal to negative 1 over a times ln of absolute value of cosecant of ax plus cotangent of ax plus c. And they just give that to you in the section. It's just like, hey, just in case you need to know this, here it is. Of course, in our situation, what is the a? 1. So I hate this because in just a couple sections, we'll learn how to do this. So I don't like using just like formulas like this, but here we are. I will have to take this off of the list of things I assign for next time because I hate this kind of thing. Okay, but a is 1. And so we could rewrite this as the answer is negative 1 over a, but a is 1, so that's just negative 1, so minus ln absolute value cosecant of ax, or cosecant, of x plus cotangent of x evaluated from pi over 4 to pi over 2. Correct? All right, and then you can plug things in. Yeah, we're so close to actually being able to show that it's true that it is painful to me that we would do it now, but it's okay. So we plug in the pi over 2, and we get minus ln of absolute value cosecant of pi over 2. What is cosecant? 1 over sine. What is sine of pi over 2? 1. So 1 over 1 is otherwise known as 1. Plus cotangent of pi over 2. Cotangent is cosine over sine. Cosine of pi over 2 is 0. So 0 over something is plus 0. Okay. And then we subtract minus ln absolute value pi over 4. What's cosecant of pi over 4? That's 1 over sine of pi over 4. Sine of pi over 4 is root 2 over 2. So 1 over that is 2 over root 2. So you just flip it. But 2 over root 2 is root 2. So the square root of 2 plus, and then we have cotangent of pi over 4, which is cosine of pi over 4 over sine of pi over 4. But those are the same thing. Those are both root 2 over 2. So root 2 over 2 divided by root 2 over 2, 1. So let's see. What's the natural log of 1? 0. So we get negative 0, or 0, plus ln of, I guess it's, the square root of 2 plus 1 is already positive, so its absolute value is also positive. So it's just the square root of 2 plus 1. And I suppose I don't need 0 plus. So that's it. So that, I did not like that problem because you have to use a formula that we don't know how to find yet. But we will know how to find this very soon. And it's very fun. Okay. Other questions? Yes, sure. 23. Let's look. Man, they really want to do this, don't they? It's okay. So I could go through this again, but actually 23 is very similar to this one. The only difference is you have to do a U substitution first. So first, if you U substitute for 3e to the x plus 4, and that's your u, then your du is going to be 3e to the x, right? And so now you just put a 3 in, a 1/3 on the outside, make the U substitution, and you're going to end up with cosecant of u du with a 1/3 on the outside. Then do this again. Okay, so I could go through it all again and use the formula again that they gave you for cosecant, how to take the antiderivative of cosecant of u. Does that make sense? A is just a constant. So it might be the number 2, it might be the number 14, but if it has a constant attached to it, just keep that constant the same as A. Yeah. And in this case, it will not have a constant attached. Any other questions? All right, well, this is kind of the chapter of how to take integrals. So the last chapter was all about what are cool things that we can do with the integral. We can calculate work and fluid force and volumes and surface areas and lengths of things. We can do all these cool things. Now it's like, yeah, but what if the antiderivative is kind of hard? Like this one, for example. What if the antiderivative is kind of hard? I don't know the antiderivative. And if it wasn't for the book saying, hey, I'm going to be nice to you, it's this. How would you do such a thing? Well, this chapter is all about, well, how do you integrate if the integration isn't just trivially, not to say that everything we've done so far is trivial, but we know the antiderivatives. If you don't know the antiderivative, what are some tools to use? And I like to think of this as like the toolbox chapter, where right now we basically own a hammer. And so when we see an integral, we do what? We take out the hammer and we go to town, because that's the only thing we have to use. We just know our basic antiderivatives and that's it. But now what we're going to do is say, oh, well, there actually are some other tools that you can use on integrals. Well, you've got the wrench and you've got the pliers and there's other things you can do. So we need to learn some of the other tools. And then you have like this whole toolbox so that when you come up against a problem, you could be like, well, how about this tool? That doesn't work very well. How about this tool? Oh, that didn't work either. Oh, take out the screwdriver. Oh yeah, that was the right tool for the job. So that's good that we just develop more tools to have in our bag of tricks, so to speak, for when we encounter different integrals. Okay, that is it for today. So for next time, I'll expect on Friday that everybody has looked over the lectures for 8.2 on integration by parts, and I will answer questions over integration by parts Friday. Until then, have a good day, and I will see you on Friday.